Welcome, everybody. This is the monthly Walk Massachusetts Network meeting. Today, we're joined by Alex Epstein, the Senior General Engineer from the USDOT Volpe Center, who will be talking about vehicle design and visibility. Alex, over to you.
All right, let's see if the video is working. All right. So thanks, everyone. Great to meet some of you and see some of you again. Let's make sure the screen share indeed works and proceed. Just let me know if at any point audio or video are less than optimal. But thank you, Walk Massachusetts and Brendan, for the opportunity to share some of this work with you. Again, my name is Alex Epstein. I lead a team of researchers at the U.S. Department of Transportation's Volpe Center in Cambridge. So this is always a pleasure to present locally. Obligatory disclaimer: I'm not speaking on behalf of the U.S. government, and the U.S. government assumes no liability for the contents of what I'm presenting here, and these are best technical judgment of staff here at the USDOT Volpe Center based on an independent and objective technical analysis and expertise, not to be misconstrued as statements of USDOT policy or guidance. All right, having pointed that out, let's jump in. So I think everyone's generally familiar, I suspect, in this group with the blind zone problem as it stands as a safety issue, as a contributor to traffic safety challenges that we face on our roads. But I'll also speak a little bit more just to level set that conversation about a way to visualize it, and then why direct vision matters and what direct vision is, what that has to do with the design of the vehicle, the design of our streets, and who's doing what about this. Also mention a specific tool that our research team has been working on for a few years now and continues to develop, called the View Blind Zone Calculator. Also mention a recent partnership with the city of Boston. So first, just to lay it out, what's the blind zone problem? Very helpfully, recently, Federal Highway Administration put out what might be the first PSA on this issue from the USDOT, as far as I'm aware, pointing out that pedestrian and other vulnerable road user fatalities have rapidly increased in the last couple of decades, and just for the first time, in a way, acknowledging that a factor there is the blind zones of vehicles. In other words, the design of the vehicle, not letting the driver see people, including children, around the vehicle, and then contributing to fatal or severe crashes. And as a way to all be on the same page, I think this is a helpful graphic, or can be a helpful graphic. So everything in the green, if you're a driver in a vehicle, in this case, a large vehicle, everything that's in the green area looking out the windows of the vehicle is direct vision. That's where you can see through line of sight. You can see a person out there walking or rolling or biking. And that's as opposed to indirect vision, which are the mirrors and the cameras that a vehicle may have. Those are shown in purple here. And so where's the blind zone then? Well, that's everything else. The blind zone, here shown in orange, is where the vehicle physically obstructs the visibility of anyone outside the vehicle to the driver. And this blind zone can vary a lot in shape and size, and especially in towns and cities where the roads are shared, this can be a pretty big challenge. From the outside of the vehicle, here's what it might look like. This one, we're out there working with the city of Boston, measuring their vehicles. More on that later. From the driver's eye point, that orange triangle on the left shows how far the ground might be in front of a truck before the driver can see the ground, before they can see the roadway. Or looking out of a vehicle on the right, there's the blind zone extends out the passenger window as well. The way this can actually play out in real life is multiple ways, either in turning crashes, or these can unfold in vehicles starting from a stop. These can be really horrible situations that are preventable at the end of the day. Now, the person on the right who was struck by the driver of that large pickup truck during a left turn was able to walk away. The woman who crossed in front of the cement truck on the left did not walk away. And these are just two examples of how blind zone related crashes can unfold. And just putting that into context, you can start counting up, and many, I mean, this has become, I think, entered the mainstream consciousness. How SUVs and pickup trucks increasingly have large blind zones that can obscure a dozen or more children in front from the parents sitting in it. This isn't even just for obscuring individual children or other, people outside the vehicle. It can be entire vehicles. Here's an example of a vehicle disappearing, so to speak, behind the blind zone of a large pickup truck. So first thing we might, each of us might ask ourselves is the market already addressing this? Are they doing something to resolve this challenge? And well, the awareness is there. Here's a large truck manufacturer showing how the driver can't see in this work truck virtually all of an intersection. That's those downward visibility sheets show where the limit of visibility is for the driver, and the roadway is mostly below that visibility sheet. We also know vehicles are, well, they're getting bigger. The consumer vehicles are growing, not shrinking. So we need to understand why direct vision matters. And as you saw before, direct vision is what a driver can see directly through the windows outside the vehicle, making eye contact with people outside, with people walking or biking. That's like you can see in the blue triangles at the right. One reason it's really important to do that, as opposed to, for example, seeing people through mirrors. You can put up more mirrors for sure, but the reaction time based on the research is going to be 50% faster if a driver can see with the naked eye. If they can see a person outside, they can stop significantly faster, and that can be the difference between running them down, running the pedestrian down, or not. To put some numbers around this, the data has challenges, and the data has imperfections. But what we do know, based on the best available data, is blind zones are at least the second leading cause of truck pedestrian crashes in the UK, and at least 1 out of 4 fatal crashes between pedestrians, cyclists, and large trucks in the United States. This is something the NTSB has addressed in the past and issued recommendations about 10 years ago, in fact. And piecing together what we can sort of put a lower limit of at least 650 fatalities a year, at least 15,000 injuries. In my professional opinion, that number is likely significantly higher. And the Insurance Institute for Highway Safety and Consumer Reports are all starting to see this, and in their analyses, especially pickups and SUVs being more likely than cars to be in crashes involving pedestrians, especially when turning. And we know the pickup truck hoods are getting taller, not shorter. So how does this play out? I showed you a couple of videos there. I hope they weren't too disturbing. The point is to I hope they're valuable just to understand how these crashes unfold and why, again, blind zones are a key factor. So this is something that hopefully it'll come through. I'm going to show these 2 videos. This is from a driver simulation study that our group led last year and published in a paper. And these are the exact same simulated crosswalk at a signalized intersection. People crossing from right to left, left to right, and then the signal's about to change from red to green. And in some of the cases, we have one person, this boy, I'll play it again, this boy in the red sweater at the bottom, who doesn't make it all the way across. They're stranded in the crosswalk. So the only difference here is one driver is stopped at the crosswalk, at the stop bar in front of the crosswalk, in a low vision truck that doesn't allow them good good sight lines down to the crosswalk. In fact, the entire crosswalk is gone from view. The other person in the simulation is sitting in a high vision truck, designed more like an MBTA bus, for example. And these are commercially available and for decades in Europe, but at least in the last few years, also in the US. So the little boy there is stranded. So what do you think happens? Well, out of 15 times that the simulation is run with 45 different subjects, human subjects, some of whom were professional truck drivers, not most, but the truck drivers didn't do any differently than regular people. Out of 15 times, they could have run over the pedestrian in the crosswalk. The drivers of the low vision truck did when there were five pedestrians crossing. When there were only 2 pedestrians crossing, 14 out of 15 times. And when there was only one person to keep track of, in theory, someone could keep track of it in their mind, right? Someone entered in front of my vehicle and they didn't make it out the other side. They still 10 out of 15 times would run them down when the light turned green. This is in contrast to 0 out of 15 times in the high vision truck. So direct vision really made a big difference, and this is described in our paper published last year in TRR. There's no reason to believe that it would be any different of an effect with a large pickup truck as opposed to a commercial truck. So if we're all if we all agree that direct vision is an important consideration for safety of vulnerable road users, people on the outside of the vehicle, how do we measure those blind zones and the amount of direct vision afforded to a driver? Well, that's the purpose of this tool that we've been working on. First started as a university partnership, and then we've been working on it since 2018. And this is a free tool. You can go online. I can put the link in the chat. And you can enter any vehicle. You have to sit in the vehicle and take a panoramic photo from the eye point of the driver and take a couple of measurements. But what it provides you is an estimate of how many either adults or children or people in wheelchairs or bicyclists, either adult or child, can fit in the blind zone forward, to the right, and ultimately all around the vehicle. Just to decode what the outputs of the tool are, this green area is where the surface of the road is visible. Black area is where the surface of the road is not visible. And then each of those white dots is the type of vulnerable road user you've selected, in this case, elementary school children, that shoulder to shoulder could be tiled and still not be visible to the shoulder or driver in that vehicle. And here it's estimated to be 176 elementary school children not visible, and the road is estimated in this vehicle to not be visible out to about 24 feet in front of that truck. So there's a QR code. I'll also share a link. I thought it might be of interest to you all to share what different groups around the world and closer at home might be doing around this safety issue. For SUVs, pickups, cars, there's a United Nations regulation called Forward Field of Vision, UN Regulation 125, that governs what the minimum field of view is. The same is true now for large trucks. It's UN Regulation 167, commercial vehicle direct vision. But those are not abided by in the US market. So there are a couple of other US, well, there's one that I'm aware of, which is the APTA bus procurement guide. That's for transit buses. So the American Public Transportation Association does have a forward field of view. You have to be able to see a certain height pole at a certain distance in front. So it's a very simple test. And then London has been really the leader globally, and they're the instigator for that UN Regulation 167. They started back in 2016, 17, implementing a direct vision standard, which came into full force last year. And that requires trucks entering the capital district in London to adhere to a minimum visibility so that they can see, especially bicyclists, but also pedestrians outside of the trucks. The London example has relied on this type of star system where trucks are rated from 1 to 5 stars, or actually 0 to 5 stars. And then once the system came into effect, 0-star trucks were banned from Greater London. And they have seen even in that first year of implementation, a significant reduction in truck-involved serious injuries in Greater London, which is encouraging. You can see how that converts to how far can you see a pedestrian at different distances from the driver for a 1-star, 3-star, and a 5-star at the bottom, going from poor to excellent visibility. And you can imagine how this starts making a difference in close quarters in a city or town environment. Montreal has also been, we've been talking with them, has also been working on this. How do we bring this to North America? And they've been thinking about mapping the visibility to different intersections in downtown Montreal. And so that's a relatively recent conversation that we've been having with Quebec. And then once we know this, there are a couple of approaches. We can change the design of the road. There's a whole toolkit that, depending on where you sit, if you're responsible for geometry or pavement markings and operations, traffic control devices, and planning different priority networks like safe routes to school and bike networks and truck networks, you can start thinking about there is a toolkit there. If we take the vehicles for granted that they're getting larger, and we have to be aware of their blind zones, there may be ways we can position road users in space and time to keep them safely out of those blind zones. And Seattle's an example of a place we've talked to that has done just that. They have, I believe it's called Marginal Way. It's a single corridor from Seattle to south of Seattle through their industrial zone. And there is no alternative for either the truck or the bike priority network. And so they are accommodating this. They've spent significant resources to bend these multi-use paths around. You can just see in the satellite images around those large blind zones of trucks entering the ports. Now you can't maybe imagine doing this in downtown Boston or Framingham or anywhere else necessarily because of the real estate. But that's the kind of geometric solution you can imagine with the vehicles we have today. If you haven't read these two reports, we talk about this and about direct vision, especially in the downsizing one that NACTO put out a few years ago. And some of that analysis is still pretty fresh. This was before we had the View app. So I think it brings together how this is both a vehicle design and a street design challenge. But if you start superposing where those blind zones fall on bike lanes and crosswalks, it can be fairly eye-opening, and just how different those are even across two different dump trucks. And never mind if we start asking, well, what about tomorrow's vehicles? Like, let's say you have this type of electric truck, where would the visibility fall on a typical intersection in Massachusetts? So we started we started going down this road with City of Boston, and I don't want to in any way steal their thunder. So this is just what we've shared at the NACTO conference last month. But over the past 6 months, and I think I see possibly a former City of Boston person in the audience, so feel free to speak up in the Q&A or in the chat. But yeah, very exciting collaboration here, where City of Boston has been thinking about this as well, and reached out to us, and we worked together over about 6 months, measuring their vehicles and thinking about what's a framework. We're not going to be London tomorrow, but what is a reasonable first step for starting to grapple with this challenge? And we measured public works vehicles, school buses, and fire apparatus, pickups, everything in between, and put together a simplified method for now. If you have to crawl before you walk and walk before you run, well, maybe this is the crawl or the walk. We realized that if you take commonly available traffic cones, it's possible to set up a simple method of measuring essentially the shoulder height of an elementary schooler and an adult, 5th percentile female in both cases. And then this could be this so-called cone method we could apply and start mapping out and see how far out the driver cannot see an adult or an elementary schooler in a crosswalk. And so standard crosswalk for, these are the MUTCD dimensions, but Boston doesn't, and other Massachusetts towns, I don't believe, diverge too far from that. Typically, you'd have the stop line only 4 feet before the start of a crosswalk, and then the crosswalk may be 6 feet wide. Some intersections, there's more of that. Cambridge tends to follow the NACTO guidance and move their stop line back about 8 feet. But the high level picture here is there's a wide range. There's a wide range among the work trucks. I mean, both this one, you know, the Mac MRU and this International Work Story, they're both heavy duty trucks, but the visibility is not the same at all. You can also start noticing here that for several of these vehicles, a child is not going to be visible anywhere in the crosswalk, even if the truck driver is doing everything correctly. In other words, they're stopping with the bumper right at the stop line. They're not even rolling in, you know, past the stop line. They're not rolling into the crosswalk. Just the design of the vehicle. And this is based on a 6 foot tall driver. It's based on my eye point. So this does not necessarily take into account shorter driver. The good news here is school buses generally are designed to let the drivers see small people, to see children. So the good news is we know how to design large vehicles that have excellent visibility. They're called school buses. And so you can start asking questions based on that. Why? Maybe, you know, how might we apply those principles of vehicle design for school buses to other vehicles? And we did the same exercise here, the same type of analysis for the bike lane, and in a buffered bike lane condition, which is not even maybe a typical condition these days. But for a buffered bike lane where there's a 2 foot buffer before a 5 foot wide bike lane, and you have an extra foot in terms of your excess travel lane width, as you say have a vehicle going down the middle. Again, this was actually quite horrifying to the Boston staff when we show this analysis. And I remember we were really thinking, how do we present this in a meaningful way to be able to differentiate among vehicles? Again, the good news is those school buses, they have a door that has a window that comes all the way down, which means that the driver can see right up to the edge of the bus. But that's not true. Once you start going into the, especially the heavier trucks, some of them, they can't see an elementary schooler out to 17, 18 feet. That's way past the bike lane. So that was definitely it made an impression on us as the researchers, and on Boston as the our partner, close partner on this. These are entirely draft. This is what we shared at NACTO, and it's entirely up to the city of Boston how to proceed. But there is some contemplation of how to act on this, and this is a possibility that will be presented for consideration. So how might a star rating system be applied in the context of a crosswalk and bike lane framework? If we assume that it is, if we take it that a driver should be able to see a child in a crosswalk if they're doing everything correctly. So based on that, this type of a star rating is one way that vehicles can be differentiated. You can imagine then that being an input to procurement, being an input to contractor, being an input to potentially future other policy avenues. And the same for the bike lane. So again, going from highest direct vision to lowest, start potentially binning them. This is how we propose potentially doing that for the side visibility. So that's hopefully, is a way for, is one way forward for addressing this issue. We're going to continue working with, we have some current research ongoing to determine how vehicle blind zones have changed over the last 3 decades for the same model. So we're doing some foundational research. At the same time, now we're excited to continue our conversations with and collaborations with Boston, with Montreal, and Quebec, and just seeing how we cannot reinvent the wheel, but indeed bring safer visibility vehicles across municipalities, across the state, and just as well as work with industry. One thing I didn't mention is there is a nonprofit called Together for Safer Roads that's been quite active in this, and they've also been a great partner. And they brought on some of the major fleets like Republic Services and Anheuser-Busch into this conversation. Some of the safety leads in those companies do see the value and the importance of this, and have been starting to measure the blind zones of their fleets. So that's an exciting development too. But here are a couple of next steps I'll plug. We do have a mailing list, so just either email me or blindzone@dot.gov. We'll add you to our newsletter. And if you're interested in taking 10 or 15 minutes and doing what Ella Froggatt from the city of Boston is seen in the photo they're doing there, we'd love to crowdsource some help as well as we build out a database of vehicles. That's what I have. I'll stop there, and over to you, Brendan.
Great. Thanks a lot, Alex. I'm going to stop the recording.